of y over x. Or if I want to go the other way, x equals r cos theta, y equals r sine theta. Hopefully you remember this. We will later on, when we do multiple integrals, be looking at different coordinate systems in 3D, and these polar coordinates will come back. But this is simple enough. It's easy to set up a map between two things. Let's talk about what the derivatives are. So suppose I have some function that is a function of f of x and y. Then I can go back to my chain rule. Now, instead of finding the total derivative, I'm finding the partial derivative. Doesn't matter, the rule is the same, because remember, the partial derivative is nothing but freezing everything and treating what's left as a total derivative, so total derivative rules still apply. Gives us partial f partial x, partial r, plus partial f partial y partial r. And we get the same. So now we have two things. And believe it or not, that's kind of the important observation here. It doesn't seem like much, but it's going to let us see something pretty useful. Because we have a linear system of equations. What's a really sensible way to write a linear system of equations? Matrix form. Did I write matrix form? Yeah, okay. I'm no longer impressed. Partial f partial r, partial f partial theta is equal to partial f partial x, partial f partial y, times by, now we have a 2 by 2. And this 2 by 2 is quite important. We will name it on the next slide. And it's a way of recounting all of the derivatives in a transformation. And in fact, this should come as no surprise. Anytime you do any kind of linear transformation in mathematics, you should expect to see a matrix operation sitting underneath it. And furthermore, when someone gives you some math and there's a matrix operation sitting there, you should think, what linear transformation gave me this matrix? So when we teach the mainstream classes how to do things like coordinate changes and integrals, and we say, go calculate the Jacobian, which is, of course, this, then they go, cool, great formula, do the Jacobian. You should be thinking, there's a Jacobian, that means this is a linear system, that means there is a linear map. What is mapping here? Matrices sometimes appear in really weird places, and it's just like how pies scattered around suggest that there's probably a circle geometry somewhere. Matrices scattered around suggest there is probably a linear map in your theory somewhere. So it's a good little footprint to look for. Okay, so this suggests a certain amount of matrix representations of derivatives is on the cards, and it sure is. But what about generalizing f? Because up until now, this is all just smart ways of looking at stuff you did last year. Let's push forward a little bit. Let's talk about a very specific kind of output. So this is a situation where f took in two variables and spat out a scalar. A vector field is simply what happens when f takes in variables and maps them to a vector. So this defines a vector field. And a vector field takes in variables and spits out a vector. So in some sense, you can think of it existing at every point and having a vector value at every point in whatever your input is. We will focus on Rn, so let's say of Rn. And vector fields are quite nice. So now f is f1 of xy, f2 of xy. Out of curiosity, is anyone here majoring in physics as well? Yeah. Okay. Everything is a vector field. Magnetism, gravity, electrical fields. Everything is a vector field. But it's not just physics. It's a way of thinking about solutions to ordinary and partial differential equations. It's a way of thinking about surfaces themselves. Vector fields allow you to describe a much, much vaster array of mathematical and physical phenomena, but accordingly, the treatment of them is a lot more finicky. So we're building the tools we're going to use later this semester. And to handle a vector field, we want what I just referred to as the Jacobian. And a shorthand for that is to call it J, or df, or partial f1, f2 over partial xy. And it's kind of what we wrote down before. Partial f1, partial x, partial f1, partial y, partial f2, partial x, partial f2, partial y. And it encodes all of the differentiations you expect to see. It is a 2 by 2 matrix in this case. The rows are your outputs, and the columns are your inputs, and I guarantee you that 5% of you will mix that up in the exam. Rows are the output, columns are the inputs. And, you know, doesn't have to be 2. Could be f1, f2, fn, x1, x2, xn. So you can have, doesn't even have to be a rectangle. Yep. Sure, but we've got to keep it consistent. Once we define it, we're going to define a lot of things that depend on it. And sure, you could go through all of math and switch rows and columns, but I don't recommend it. It's like the right-hand rule. At some point, you just got to pick something. Okay. So this is a way of thinking about partial derivatives of vector fields. And it's going to be part of the natural language that we're going to start to incorporate. It layers on, because we were talking about changes of variables, and this is where it becomes very neat. So in this case, everything depended on x and y. We have a 1 by 2, because we have 1 output, 2 inputs, times a 2 by 2. If all of your transformations are consistent, then you should be able to sequence these. And that's when you're starting to do chain rule stuff. Except now, instead of the chain rule depending on t, our chain rule depends on u and v. So now our chain rule has 2 variables. Well, using the chain rule, this is partial f, partial f1, partial x, partial u, plus partial f1, partial y, partial u. So that's just the chain rule expansion of the 1, 1 term. And you can do the 2, 2, and the 2, 1, and the 1, 2, and you can get out a 2 by 2 vector which is full of chain rules. But actually, a nicer thing to do is to break this into 2 matrix multiplications. The first is our Jacobian from before. Partial f1, partial x, partial f1, partial y, partial f2, partial x, partial f2, partial y. And our second map is going from the x dependence to the u dependence, gives me partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. So instead of writing out big, horrible, long chain rules, they're just sequences of matrix multiplications where each matrix is telling you the effect of that transformation in its local region. And picking up on this notation we have here, this can actually be written in a very nice form, which is partial f1, f2, ... fn, partial u1, u2, ... um, no obligation for them to be the same, partial f1, f2, ... fn, running out of letters, partial x1, x2, let's go k, partial x1, x2, ... xk, all over u1, u2, ... um. This is an n by k matrix. This is a k by m matrix. This is a consistent matrix multiplication. So this is quite neat. So what we actually have here, if we wanted to apply that, was this is partial f1, f2, partial xy, times by partial xy, partial u, v. So it's a nice way to think of derivatives of vector functions, of vector fields. And vector fields are going to be the super important ingredient that the rest of your semester will roll around once we get past a couple of weeks of groundwork. Okay, I bet we can make this nicer. I bet we can talk about this a little easier, especially to begin with if we forget about vector fields for a while and go back to scalar outputs. And of course we can. From the chain rule, remember that if we have f, x, y, z, and we want to find the derivative of du dt, why did I write that as f? U. And we want to find du dt, that is partial u, partial x, partial u, partial y, partial u, partial z, times by x dashed of t, y dashed of t, z dashed of t. We wrote this out a few times. Now, this formulation appears in mathematics quite a lot, so much, in fact, that we give this thing a name. And we call this grad of u, or the gradient of u. I know you've seen the gradient operator before, but it's a good time to remember what it does. I will not put the underbar under gradient operators. You know it's a vector. Well, it's vectorish. This is called the gradient of u. So we've been looking about how u changes along some curve, x of t, y of t, z of t. And this is a really important piece of information. This allows us to codify it in a really, really nice way. Because I can now write that as a dot product. So I have du dt is equal to grad of u dotted with gamma of t. But of course, u depends on x, y, and z, which depend on t. So d dt of u of gamma of t, because u just takes in gamma as an input, is gamma of u of gamma of t, dotted with, sorry, this should have been that, gamma dashed of t. So we took gamma dashed, put it there. We took the gradient, we put it there. And what we get is something that looks remarkably like the single variable chain rule. And this is not a coincidence if everything sort of falls down to that in one dimension. This looks like the one variable chain rule, because that's what it is. So if we what this sort of suggests is in some way this definition of the gradient is the right way for us to think about the variation along a curve. But if we go back to what we know about partial derivatives, and I'm not scrolling all the way back to slide 4, they tell us how something varies in the x direction or the y direction. With the gradient, as I hope you remember, we can start to generalize that a bit and talk about any direction, just by picking out gamma to be moving in that direction. And the way we're going to do that should come hopefully as no surprise, although possibly a small amount of trepidation, is talking about level sets. Because the gradient is very closely related to level sets, at least as we start to unpack what it means. After this, we will probably not talk about level sets anymore, I promise. So we have some u of x, y, z with a level set, u of x, y, z is equal to some constant value c. So if you're a little bit rusty, or we're hoping to never hear those words again, a level set is the set of all values which have the same height, same altitude on the mountain. So u of x, y equals c. And what we're going to do is define our curve to be one that stays on the level set. So we have our gamma of t, and it's just moving along the level set in some direction. Gamma of t stays on the level set. What does this tell us about gradients? Well, level sets and gradients are best friends. They tell you everything you want to know about each other. So we're going to define gamma of t equals x of t, y of t, z of t. Lives on our level set, so it's a specific choice of gamma. Everything we did in the last few slides is talking about nice general gammas, but now we are talking about a very specific restriction. But we are going to use the fact that we know that du dt, the variation of u, is equal to gradient of u dotted with gamma dashed of t. So we've already shown that. We don't need to relitigate whether that is true. But of course, u's not changing. So as I move around a level set, u doesn't change. And since u doesn't change, this is 0. And that tells us about the relationship between our level curve and our gradient, because they must have dot product 0, which means they must be orthogonal. I'm about to write all that out, but everything I'm about to write is sort of hovering around that point. We know du dt is equal to this, and we also know that du dt equals 0 on a level curve because u is equal to c, which is constant. So u's not changing. So if we recall our definition of the tangent space at some point p of u is equal to the set of vectors such that the vector is equal to gamma dashed of u, and gamma of t has u equals c. That's our restriction that gives us our curve. And of course, gamma of naught equals p. So we're saying it lives entirely on the level curve. Then, if gamma u dotted with chi dash of naught equals 0, what does this tell us? So it tells us, in geometric language, that the gradient vector is orthogonal to level surfaces. So if I can find the level surface, what I do is turn 90 degrees, and then I am pointing in the direction of my gradient. These are orthogonal. If you know one, you know the other. And this next one is just putting that idea into linear algebra terms. Let me write this, and then I'll ask you. Going to put that idea in linear algebra terms. The tangent space is the null space, or kernel, of the linear map defined by our inner product. The tangent space is the null space of this map. Yeah. The direction. Yeah, but you can find the space because it's the set of all of them. But the gradient is not, because remember, the direction of the dimension of the tangent space is the same as the direction of the surface, so the gradient's going to be restricted to one direction to fill out. Because if you're in Rn and your tangent space is Rn minus 1, then its orthogonal space has to be one-dimensional. So it will uniquely define the direction. Yeah. Yeah. So that's nice. This says this in words. Don't, we want to keep tying things to linear algebra. These are two interpretations of the same fact. Pick whichever interpretation speaks to you. Good. Okay. So we now have the gradient, which weirdly means we have another way of working out our tangent space. So let's retread an example we did before and see if we can pull out the same result using this body of theory. And because I could never pick the easiest example, I've picked this one. Let's take another look at the tangent space of SL2, but see what we can do now that we have the gradient operator at our disposal. Can we use this approach instead? Well, we need to find a level set. And actually, the reason I chose this one is because the level set is incredibly nice. Hands up. This is maybe the first slightly tricky question, so don't yell it out. Hands up. What is the level set? What's the definition? I don't mind you being wrong, but I want someone to try. Go on. The level set that, so if I want to define, so I'm taking the set of all matrices, and I'm saying that this set is a level set of that. What's the level set? What is the definition of that level set? We only really know one thing about this set. Yes? So not quite, because that will actually restrict this set, but good try. Yep. So SL2R is defined by the fact that its determinant is 1. So we can say that it is defined by the level set AD minus BC is 1. So we are going to make that our level set, the set of all outputs that satisfy this. If you like, you can say that D is equal to blah, blah, blah. So we have a level set. AD minus BC is equal to 1, so this is the function I'm going to call U. Level sets are just constraints. We will do Lagrangian multiplier optimization later in the semester, and we will talk more about constrained optimization. Level sets are just constraints on a bigger set. So we have taken the bigger set of all matrices, and we are constraining it by picking a level set to AD minus BC equals 1. Sometimes these can be a pain to construct, but actually this one is very, very nice. Because now I can construct grad of U. Partial U, partial A, partial U, partial B, partial U, partial C, partial U, partial D. Which is equal to, all right, partial U, partial A. Take the derivative of U with respect to A, I get D. Because remember, this is U. This thing is U. So the derivative with respect to B minus C, the derivative with respect to C minus B, and the derivative with respect to D is A. So now I've got my whole set of matrices, M2. I have used a level set to restrict it to the members of SL2 only. And now I'm looking at the gradient on that level set. Defining a bigger space and using a constraint to restrict it to things that you're interested in is an incredibly powerful mathematical technique that you will use again and again. We often come up with all manner of ways to embed the space we're interested in a bigger space. When you do analysis and complex analysis and weirdly, surprisingly, fluid dynamics, you'll see a lot of cases where we take real fluid flow and expand it out, or real whatever, and expand it out to be complex so that we can then suitably restrict our space but say interesting things. Embedding things in bigger spaces and then applying sensible restrictions is a really common mathematical tool that you will see again wearing different clothes throughout your studies. Okay, so we are not interested in the gradient everywhere. We are interested in the gradient at a particular point, which is the identity. 1, 0, 0, 1. So in this case, A is 1, B is 0, C is 0, D is 1. And the gradient of U, D is 1, C is 0, B is 0, A is 1. So now I'm talking about the way in which my set SL2 is changing within the 2x2 matrices, and I'm using multivariable calculus to talk our way through that. Hard to visualize. Follow the definitions. So the tangent space is the kernel of the map defined by the grad U inner product. If V is equal to, and I don't know what V is, so we'll just say V is some arbitrary thing, and grad of U dot V is equal to 0, then I know that it's going to lie in my tangent plane, because that was the linear algebra definition of the tangent plane. Then, what I'm actually finding is 1, 0, 0, 1 dotted with alpha, beta, gamma, delta is equal to 0, or alpha equals minus delta. Exactly the same condition we found before. So this is another way, exploiting the relationship between level sets and the gradient operator, to pull out this same information. We like tangent spaces. So therefore, all vectors A, B, delta, A, B, gamma minus alpha satisfy our condition. Therefore, all matrices, spell that correctly, alpha, beta, gamma minus alpha lie in the tangent plane. And as a reminder, these are the zero trace matrices. So exactly the same thing. All of these ideas are different tools of looking at the same fundamental idea, and they all relate to each other. But we like a bit of geometry. It makes things easier to visualize. So maybe let's take a step back. Let's think about this definition again, and let's attach geometric notions to it. So our geometric meaning, we have that du dt evaluated at t equals 0 is equal to grad u of p dotted with gamma dashed at 0. So, as a reminder, what that means is that we have some gamma of t which is a path, and I will talk about that one in a moment. X, y, y, and u. And when we put it on our graph, it looks like this. So we have some path. And we'll talk more about what the specific path for this interpretation is in a moment. So I'm going to say, look, at gamma of 0, I have x dashed of 0, y dashed of 0, z dashed of 0 is equal to my vector v. Okay. And gamma t is chosen such that the norm is 1 because we don't want a whole bunch of normalizations floating around. You can always choose your parameterization such that this is true. We will prove in week something that that doesn't matter very much. So we can always choose a t parameterization such that the appropriate v can be normalized to 1. Then we know that du dt evaluated at t equals 0 is simply this, dotted with v. So what that is how much u is changing if it is pointing in the direction v. So what I'm going to say here is that this ut is equal to u of 0 plus t times v. So I have my u of p, which translates to a point on this straight line. And what this tells us is that the change in u as we vary along t is simply equal to the projection of the gradient on the direction that we care about. Now this, I think, is almost always the one thing everyone remembers from 1962. So good. If you don't remember, good to know. What this allows us to do is take what we know about the partial derivatives and generalize it to any direction. Maybe I don't want to know how my surface is changing in x and y. Maybe I want to know how it's changing halfway between those two things. I simply pick out my v and normalize it so that it has length 1 and project down onto it. So the gradient doesn't just tell us about the directions that have names. It's very inclusive. It tells us about all of the directions that we have available to us. Let's do a little bit of theory just to remind ourselves of what all this means. We're going to start by using the Cauchy-Schwarz inequality on this. So we're going to say, all right, from the Cauchy-Schwarz inequality, we have that the absolute value of u of p dot v has to be less than or equal to their independent norms. V, and of course, because we were judicious about picking our v, this is a unit vector, so v is 1. It is strictly greater than 0 because they are not orthogonal. It's 0 if they're orthogonal. Why did I put... Yeah, give me a second. I may just have written this incorrectly, but I want to make sure that I don't give you something technically incorrect. I've got to be technical here. Yeah, okay. Look, we'll say this, but we are not interested in directions where we're not interested in the level set direction. If they're orthogonal, this is on the level set, where we know u isn't changing. But we'll say that. Okay, so this is an equality if they're orthogonal, which kind of leads nicely into the next bit, because there's a condition in which these are an equality. What's that condition? Sorry? Oh, I heard the word parallel. Good, yeah. This is an equality if the gradient and the direction are parallel. And this is nice, because it means that not only is the directional derivative a total information about how everything is changing, it also tells you the direction at which it is changing the quickest. The directional derivative is maximized in the direction of the gradient. Which, of course, if you remember your first year, you'll recall that grad u of p dotted with v can be written as the norm of grad u of p, norm of v, times cos of the angle between them. Since v is 1 and the magnitude of the gradient is just a value, this depends solely on the angle between them. So this is 0 when they are orthogonal, and it is maximal when they are parallel. All right, a last example. I said this week we would get you out a little bit early. I didn't think it would be quite this early, but you know, next week's have more. The future weeks have more stuff, so enjoy it while it lasts. This one's for the physicists, but actually it's not, because what I'm going to... It is for the physicists, but mathematicians don't tune out, because it's about a mathematical concept which, as I've said before, you will see again, but a very important one. And it's a concept which most people meet for the first time through physics, but if you're not a physicist, that is okay. This is not a physics subject, despite all appearances. The electric potential between two particles of opposite charge. So I have a particle here, which has charge Q1, and I have a particle here, which has charge Q2. And I'm going to say, I'm going to get you out, I promise, but let me finish. Because they are opposite charges, they are attracting to each other. Okay, so two particles hanging around. Actually, they're hanging around in a vector field because, as I mentioned, electrical fields are an example of a vector field. The thing we're talking about will tie into what that vector field is, which is one of the reasons I want to show you this. So I'm going to say this one is positive, and I'm going to say this one is negative. And I'm going to say that the difference between them is R, which is X, Y, and Z. Okay, so whenever you talk about electrical quantities, you know, you grab two wires. As everyone knows, it's the voltage. The voltage is fine. It's the current that gets you. We're going to talk about what voltage is. So voltage So we're going to say voltage is equal to Q1, Q2, over 4 pi epsilon naught times by the absolute value of R. Q1 is a number, Q2 is a number, epsilon naught is a number, 4 and pi are numbers. Absolute value of R is a quantity in our problem. So the question is, what is the radius between these two things? Or more to the point, well, we'll see in a moment. We are going to write this, because we don't like all of those numbers, as minus k over the absolute value of R. Because we are mathematicians, and if there is one thing we hate, it's an actual number. So we're going to, and because they're opposite charges, this is negative, so k is a positive real number. Okay, so what is V? This quantity V, which I've just written down, is called a electric potential. Now, we call it voltage because this is a mouthful, but the idea of a potential is going to become a very, very important one. In week 5, we are going to prove that every vector field that is what we call conservative has a vector potential. And those vector potential has a scalar potential. And scalar potentials are a way of encoding information about vector fields in a much more compressed way. Very easy to work with. And a lot of things you've probably heard, potential energy, vector gravitational potential, all of these things. These are examples of scalar potentials of vector fields. So I'm not just introducing voltage because batteries are fun. I'm introducing voltage because it is the first example that some of you will see of a potential, a quantity that we will come back to in a really important way of thinking about vector fields. So this is an electric potential. A potential encodes information about a vector field. Vector fields as scalar functions. Not every vector field has a scalar potential, and we will learn about when that is and is not the case. You will see we talk about fluid potential. You can talk about complex potential when you think about the set of complex numbers as a vector field, which you can. So all of these potentials are ways of encoding what's going on. But for now, we're just going to follow the formula, and we might come back to it when we know a little bit more later in the semester. Square root of x squared plus y squared plus z squared. Okay, so if k is a constant, what is minus grad v? Because it turns out minus grad of v is equal to the electric field E. Electric field. So just by finding the gradient of this scalar quantity, I can tell you about the vector field that is sitting underneath this system. And it's just a direct calculation. E equals minus grad of V is equal to minus partial f partial x, partial f partial y, partial f partial z, which is equal to, if you want to sit around all afternoon and calculate these out, there are worse uses of your time, x squared plus y squared plus z squared to the power of 3 over 2 minus ky, copy, paste, yeah, minus kz. That is why I have a PhD. Minus kx over that quantity, minus ky over that quantity, minus kz over that quantity. And because vectors factorize in sensible ways, we can write that as k over the norm of r cubed, xyz. And xyz is nothing but r, k r over r cubed. Later in the semester, when we learn about how to construct scalar potentials from vector fields, it'll be a really interesting exercise that I can't remember if I do or do not in class, to go back and go the other way. And to say, well, now that I know everything about why this vector field has a potential, can I use that information to construct and interpret this? And it's a good thing to do. Okay. We have come to the end. You can talk a little bit now. I won't get angry. This has been really good. So I want to kind of stress, I know week 1 is a bit revision-y. I know that you've seen tangent spaces. I know that you've seen gradients. I know that you've seen the chain rule. I also know that many of you don't remember, so if you do, allow yourself to feel a little bit smug. And the idea here is to make sure you are all back up to where we need to be. New material will start next week, although there will be a bit more revision, because we are going to start with optimization of multivariable functions. Again, linear algebra lens, but material you've seen before moving on to new stuff. Then the rubber will hit the road a bit and things will start to speed up and you'll all start to panic. But until then, thank you very much. I will see you at 12 in 273 for the seminar, or not. Your time is yours to choose. Thanks very much. Sorry, I hope I addressed your question in class after. Yeah, cool. No, that's okay. Right, it's. I didn't explain that at all. That is just illustration. So SL is the special linear group, 2 is the matrix, and R is the set. So this, we won't see other general. But yeah, that's all it is. Yes. Stand up. Just, yeah, cool. One person at a time. Yeah. Oh, that was just a picture in 2 dimensions. So the theory I wrote out in 3, but the picture was just a bit of a guide. So I just drew it out.
Yeah, just like the when you were explaining.
Exactly. Yeah.
Yeah, I think everything else I need to.
Alright, good.
I need to ask.
Yeah, no stress. Look, if you come up from basic to advanced and there are any concepts you miss, come and talk to me, and I will clarify them a bit to help you make that jump.
Thank you.
See you later. Hello.
You know how like you create, you know how I did like the A, B, C, negative A?
Yep.
Here, like what does that equation tell you?
That tells me that the determinant of the matrix is 1. So remember, this is the condition. SL2 is the set of matrices whose determinant is 1. So in some sense, it's the volume preserving matrix.
So what are we calculating here?
What we are calculating is the tangent plane to that set. So think of that set as living in the space of matrices in general.
Okay.
So you can think of that set as being a surface in this space.
So we're taking all tangents like that equation.
Yeah, we're saying that the set of tangents at the point which is denoted by the identity is given is no, because remember, it's a multivariable surface. So it's a 3-dimensional surface, so the tangent surface must be 3-dimensional. Because there's 3 degrees of freedom. I can pick A, I can pick B, I can pick C, and then D is the best form. So SL2 is a 3-dimensional surface in a 4-dimensional set.
So like there's infinite tangents.
Yeah, well, there's a 3-dimensional set of tangent vectors.
Because that's 2D and it's like in 4D.
No, in this case there is a 3-dimensional set. So in the sphere is 3-dimensional because you pick X, you pick Y, you pick Z, and then W is fixed.
Yep.
So so this is the 3 sphere, which means it's not the 2 sphere. This is S2. S3 is that the surface is 3-dimensional, not 2. You can't visualize it. You just have to follow the map. Which means that the tangent space must also be a 3-dimensional space.
You know how like in this equation, because you said like, oh wait, I didn't see that line there.
No worries. It's possible I even forgot to write it, but hopefully I didn't.
Yeah, I was gonna say like, so like this is the gamma, like the equation of the line.
Gamma is the change, it is the derivative of the line with t. So it's how my curve changes as t varies. In this construction, it's just v. but that's a special construction. Gamma is just, I've got some curve gamma, and it's how my graph changes as I follow that. It's how that line changes as I follow.
Thank you.
No worries. What's your name?
Leighton.
Nice to meet you, mate.
Meet you.
I'm sure I'll see you around.
Same.
Ciao.